Okay, students, it has been quite a long time since I have not uploaded any video lectures, but I thought that I sent you some PDFs and I thought maybe you could take your time and go through it. I will not be dealing with the derivations because it's already all given and they are all quite easy to understand now that you know a little bit of thermodynamics. So today we start with video lecture 21, and over several lectures now we will talk about this very important aspect of metamorphic metrology. The aspect essentially is taught based on progressive metamorphism of dolomitic quartzite or quartz-rich dolomite, whatever way you say it. There is a reason for it, because dolomitic quartzite or quartz dolomites, I will tell you the difference. They normally are composed of calcium, magnesium, silicon rich minerals, and they have contained a little bit of iron. So there are more the solid solution phases, but it's not really a major issue. So essentially what happens is this system, CO, MgO, SiO2, H2O, gives a very good foundation as to learn the basics of how metamorphic rocks respond to changes in pressure, temperature, fluid composition. What is the relationship between the bulk rock and the mineralogy? All these aspects can be well thought of because the system, the chemical system, CO, MgO, SiO2, H2O, is simple. And as you know from the derivation, normally XH2O plus XCO2, you will see the derivation, it is equal to 1. That is why when it writes dxCO2, it says equal to minus dxCO2. It is because XCO dx is because XH2 is equal to 1 minus XCO2. So if we take the derivative form, then it's del XH2 is equal to minus del XCO2. So that makes it very simple. So you essentially take a binary fluid of H2CO2, but a fluid present situation. You take minerals which are mostly pure. There have been a lot of experiments on this, so the stability fields are very well known. And that is why this system is chosen to teach the very basic foundations of essentially metamorphic metrology. And I will work on this system. I don't know whether to anyone this system has been taught. It might be taught to certain aspects, but there are many aspects of this progressive metamorphism of silicious dolomite, dolomitic quartzites, as it is called. There are many facets to it, and it's important for our understanding of metamorphic metrology. We see what are the importance of these aspects. And in another system, when you go, you change the minerals, but whatever you have learned, that remains. It's very fundamental. So the system that we will be talking about now is CO, MgO, SiO2, H2O, CO2 system. This is the system we will be talking about. Now you see, we start breaking up the system a little bit. Say for example, if we start with a system containing only SiO2. If we take a chemical system only with SiO2, then the minerals that you get are silica polymorphs. That's all the minerals that you get are silica polymorphs. Alpha quartz, beta quartz, quartzite, stishovite, tridymite, all these minerals you get. So you get different polymorphs of SiO2. But say for example, if you add the system CaOSiO2, remember I am always writing plus H2O plus CO2, right? Now there are no minerals with SiO2H2O system. There is no mineral that is stable at very high pressures. It doesn't occur. But when we extend the system to CaO, then you see when you extend the when you extend the system to CaO, there are fairly good number of minerals. Fairly good number of minerals. Say for example, when you add CaO, you get something called very similar CaCO3. So you have calcite and aragonite, but aragonite is not stable at metamorphic temperature conditions, so we can ignore aragonite, but you have calcite. Then you have wollastonite, for example, CaSiO3. This is wollastonite. This is a pyroxene. And then you have, say, for example, Ca2SiO4. Ca2SiO4. Say, for example, if you take the olivine structure, this is CaO, this is MgO, and this is FeO, and you have plus SiO2. Then this is phosphorite, Mg2SiO4. This is firelite, Fe2SiO4, and here you have a mineral which is Ca2SiO4. That means 2 Ca. Important is this is Ca and this is Mg. Okay, I'm making a mistake here. Just wait. Say for example, when you have this triangle Ca2SiO4, Mg2SiO4, and Fe2SiO4. Now, this is firelite, as you know. This is phosphorite, and this is lignite. This is the mineral lignite, which is Ca2SiO4. And in between Ca2SiO4 and Mg2SiO4, at this point, 50-50, you have something called CaMgSiO4, and at this end you have CaFeSiO4. So now this mineral CaMgSiO4, this is called monticelite. Monticelite. And CaFeSiO4, this is called Kirschsteinite. Kirschsteinite. So monticelite is CaMgSiO4 and Kirschsteinite is Fe2SiO4. This is a German name. Stein means a rock and Kirsch are cherries. So they are red colored minerals and they are called Kirschsteinite. And you have the CaMgSiO4, which is again colorless, monticelite, phosphorite, and lignite. So essentially, lignite is to olivine as what is wollastonite is to orthopyroxene. And monticelite is equivalent to dioxide, and Kirschsteinite is equivalent to Heidelbergite. So if I change this to a pyroxene, then this would be wollastonite, this would be enstatite, this would be ferrocellite, this would be dioxide, and this one, CaFeSiO4, dioxide and Heidelbergite. So basically, just for your information, now so when you add here CaSiO2, then you add Ca2SiO4, and the mineral name is lignite. Then you have several other minerals. These are not very common minerals, but they do occur in this. And there are some minerals which I will write it down now. There is another mineral called rankinite. And then spurite, and then tillite. So rankinite, the formula is Ca3 Si2O7 Ca3Si2O7, 3H2O. That's rankinite. Sperite is Ca5Si2O8 and CO3. So this is how they occur. Tellurite is very similar to sparite. So we have, these are the minerals that occur in the SiO2 H2O CO2 system. So if I take SiO2 only, then you have only the silica polymorph. If I just take SiO2, then you have the silica polymorphs. But if I change the system to CaO, then you get more minerals that are possible. So you get calcite, you get elastonite, you get lardnite, you get rankinite, sperite, and tellurite. I forgot the formula of tellurite. Now, obviously, all these minerals are not stable at the same pressure temperature condition, but there it is. So the moment you increase the number of components or the number of system components, the number of phases that come in become higher and higher. Now, for example, if we add to this NGO, now you will see you open up a Pandora's box. NGO, CaO, SiO2, H2O, CO2. Now you see we will write a few. We won't write a lot of them. Say for example, CaMgSi2O6. So that's dioxide. And as I told you for olivine, CaMgSi2O4, and this is monticellite. So these are calcium magnesium minerals. Then you have, for example, Ca2 Mg5 Si8 O22 OH whole twice. This is tremolite. You have a whole set of minerals now. This is tremolite, but I've been only talking about calcium magnesium. There are a whole lot of magnesium bearing minerals. Say for example, Mg2SiO4, this is phosphorite. Then you have MgSiO3, this is enstatite. Then you have Mg3 Si4 O10 OH whole twice, and this mineral is talc. There are many other minerals. Say for example, you have the mineral MgO, and you have the mineral MgOH whole twice. So this is brucite, and this is periclase. And you can have MgCO3. You can have magnesium carbonate, so you have magnesite. Now you see, in this simple system, which is a very small system essentially, it's not a big system at all. So if you increase the number of components, you increase also the number of phases. And all of these phases are not stable at the same pressure temperature condition. They are stable at different pressure temperature conditions. And not only pressure temperature conditions, also the composition of XH2O plus XCO2, which in this case here is XH2O plus XCO2 is equal to 1, which I was saying, and in the derivation it is given dXH2O is equal to minus dXCO2 in the derivative form. Minus dXCO2 in the derivative form. You have a whole set of minerals coming in. Imagine if you add aluminium to it, iron to it now, you will have another whole set of minerals, including a host of solid solution phases. Now, if you make a system very big, then you can understand the stability field makes it very, very complex to understand. So we will not do it. we will keep ourselves to a particular pressure temperature range, a small window, and try to understand the complications arising out of it, and try and get more insights into how metamorphism occurs in the rock. Right? Just to give you an idea, so CiO2, only silica polymer, CaSiO2 you added, and you add MgO and you whole added. I'm sure there are many more if I try to find, but that's about it. Makes it very, very complex. But in this case, we will not be dealing with all of this. We will be dealing with only a small part, small stable part, where there are only few mineral phases and there are few reactions stable. Right? So these are the minerals that are stable. I will just wipe this a little bit. And let's wait half a minute for it to pick up dry, and then we can start our discussion. Okay. So now let's say we take a triangular diagram. We take an equilateral triangle, which is essentially a composition space, and this is CaO. This is let me see what I have done. Okay, SiO2. This is CaO, and this is MgO. We take this compositional plane, and we remember that you have plus H2O and plus CO2. So here, for example, at this point, you have only quartz. At this point, you have calcite, CO3. So you have quartz and calcite. Well, we will say, for example, let's be on the binary for the timing, for a little time. So what are the other possible minerals in this? So it will contain SiO2 and CaO, no MgO at all. It will not contain any MgO. So you can see, let me tell you, say CaSiO3. So that's wollastonite. And then you have Ca2SiO4. This is lignite, and this is wollastonite. Now you see here, calcium is to silicon ratio is 1:1, or CaO is to SiO2. If I take this as SiO2 and this is CaO, 1 mole of CaO plus 1 mole of SiO2. So we have wollastonite at the 50% line. So this is CaSiO3. This is the plotting position of CaSiO3. But if we take, for example, lignite, then you will see this is essentially 2 CaO plus SiO2. So 2:1. The total is 3. So what we do is divide this into 3 parts. Right? So that is 33%, this is 33%, and this is 33%. And Ca2 means you have more of Ca. That means CaO is 100 here, SiO2 is 100 here. So if you go to this, then this will be the point where you have Ca2SiO4. You see, this is 2:1. Ca2SiO4. So this will be the plotting position of Ca2SiO4. And say for example, I think I plotted this a little too high. This is Ca2SiO4. And if you plot, you will see this is the position, for example. At this position, you will have sparite, rankinite, etc. would plot in this position. Slightly lower than this, you will plot the position. You can take a line and write down the ratios, and you can plot the points, and you will see that they plot here. So you have quartz, you have calcite at the end, you have wollastonite somewhere in the middle, you have lignite here, and here you have sparite, rankinite, etc. Very close spaced in that very close spaced place. And now what happens here on this? Here you see this is CO-NGO line. So if I take the midpoint here, then you see at this point there is no silicon. At this point there is no silicon. Silicon is zero. So the mineral that you have here is dolomite. What is the formula? CaMgCO3 whole twice. In the before that, what I erased, I should have written dolomite. I forgot about. Too many minerals to remember. This is dolomite at 50:50 line. You see there is no silicon because silicon is 100 here. Along this line, silicon is 0 here. So this is dolomite. But say for example, if you take, these pens are creating a lot of problems. Say if you take CaMgSi2O6, CaMgSiO2O6. So you have CaO is to MgO is to SiO2, and that is 2SiO2. So if you take the ratio, then it will be 1:1:2. That is how the ratio is in CaMgSi2O6. And if you take CaO plus MgO is to SiO2, then it is 2:2. So now, for example, if I take this point and add it up along the line, so where will it plot CaMgSi2O6? It will plot where the 50% line plots it. So this will be the position where dioxide plots. This is the position where dioxide will plot. Have you understood? This is the position where dioxide would plot. And why dioxide? Because here SiO2 is 50% and CO plus MgO is 50%. And Ca is to Mg, here it's 1:1. CaMg, they will have the same coefficients, 2:2, 1:1, 3:3. So the ratio is always 1:1. So here you have dioxide and here you have dolomite on the same line because both of them have Ca is to Mg 1:1 ratio. So we have calcite, we have dioxide, and then say for example on this side phosphorite. Where will it plot? Once again, you divide the line Mg2SiO4. So you take Mg2SiO4. So that means it's 2 MgO is to 1 SiO2. So as with this, you see this one was lignite. So this one was lignite. So if I draw a line, this should be 1/3. So this will be Mg2SiO4 or phosphorite. Then, for example, enstatite, of course, MgSiO3. MgSiO3 would be here, 50-50 line. MgSiO3, Mg2SiO4. Then, for example, brucite and periclase. Periclase is MgO, brucite is MgOH whole twice. But both of them will plot here because OH2 comes here only. It does not plot in this composition. So when I say periclase, that is MgO, and brucite, and that is MgOH whole twice, and then magnesite MgCO3, and all these three will block here. There is no distinction because all of them, OH2 is not one of the coordinates of this triangle, only MgO is. So they will have pure MgO, and all of them will plot at the same point here. So this is how things are plotted. So here, for example, you have MgSiO3, you have MgSiO3, you have Mg2SiO4, you have quartz. Now you see there we find. Let us draw this, then we will go into the other parts of more interesting parts of the diagram. But these are, I think, very essential, and that's why maybe to some people it's a bit of repetition, but I don't mind it, because I think it's best important to get things clear first, instead of going to the middle and then finding out that you're nowhere. So say, for example, in a triangle like this, say, for example, in a triangle like this, say, for example, I have this. I have, say, okay, let's do this. SiO2, CaO, MgO. Right? SiO2, CaO, and MgO. And this is SiO3. And this one here is MgSiO3, and this is here is Mg2SiO4, and this here is Ca2SiO4, and it goes on, and you have dolomite here, and you have dolomite here, and this is of course quartz, of course, and this is calcite. Now, say for example, I have a line where you have, this is at A and this is at B, and if there is a C and there is another mineral C plotting in them, then AA plus BB should be equal to C. And what is A? A is this proportion, this is A. And what is B? B is this proportion, mole proportion. So A into A plus B into B should be equal to C. That is, when your composition of a mineral plots between two minerals, then this composition can be resolved between the two end members. Two end members means two end members, and these are the stoichiometric coefficients, but this is A and this is B. Have you understood? So say for example, this is one way of doing it. It is also possible, say for example, we will do this. Say you have a line A and a line B, and you have a line C and a line D. Then it will be possible for you to write AA plus BB is equal to CC plus DD. This is called the crossing tie lines, where you have what is A, small a is this. What is small b is this. What is small c is this. And what is small d is this. These are the mole proportions. So A plus B, AA into BB is equal to CC into DD. That means if A and B reacts in a molar ratio of A is to B, then you will produce C and D in the molar ratio C and D. And this point here will be the composition of the reaction volume. Or at this point on this line, if you take this line and there is a point here, and this line and this point here, this point is common to both. Have you understood? Which means Say for example, if I remove this point and write this, and I take this point, this can be written in terms of A into A plus B into B. So this point, so that will be a particular composition. And if now I join this, then you will have CC into DD. This is the point shared by both the tie lines. This is where the composition of the reactant, what is the reactant? A into A plus B into B. That is the composition of the reactant is equal to CC plus DD, which is the composition of the product. So I told you the first case where there are two phases and you have a mineral that forms inside it on the position. So what you have, AA plus BB is equal to C. That is one thing. Or here you have what is called the crossing tri lines, where A plus B reacts to C plus D. This is another way of how to promote reaction. So not only the intersection, but the magnitudes of this give an idea of what is the proportion of AA and BB in CC and DD. They give you the proportion in which the reactants react and the proportion in which the products are produced. Then, from the phases, there is another point. Say, for example, there is a composition space given like this, composition space, where you have X, Y, and Z. And you have a mineral which is N. Then, N can be expressed in some proportion of X, Y, and Z. In some proportion of X, Y, and Z. It can be written in terms of X, Y, and Z. So it should be X into X plus Y into Y plus Z into Z is equal to N. So if there is a composition space and there is a mineral inside it, then it will be X into X, some proportion of X, another proportion of Y, and another proportion of Z should give you the composition of the mineral M, normalized to 1. So either if you take a line and there is a mineral in between, or you take a crossing tie line, or you take a line within a composite or a point within a composition space, all of these minerals, say M or BB, whatever I've shown you, they can be expressed in terms of the apices of the triangle. Apices of the triangle. Let's see now how we can, now knowing this, how we can do things. Say for example, just for fun, let's say here I have calcite. Say I take calcite. I will take another pen. Say I take calcite and forsterite. You see, I join calcite and forsterite. But you can see, I can write this also. Do you see that? So I can have a reaction CaCO3 calcite plus Mg2SiO4. This can give you calcite plus Mg2SiO4. This can give you Ca2SiO4 plus CaMgCO3 whole twice. And this can be balanced. Let's see how we can balance. So you see there is magnesium 2 here. So the first is we have to do the magnesium here. So we have now 2 magnesiums here, and here is 2 magnesiums. And you can see 1 silicon here and 1 silicon. So silicon is balanced, magnesium is balanced. Now look at here. You have 2 calcium plus 2 calcium, 4 calcium. Here you have 1 calcium. So you will have 4 CaCO3. Now you see here 4 calcium, 4 calcium. Here it is 2 calcium plus 2 calcium, 4 calcium. So calcium, magnesium and silicon are balanced. What is not balanced is carbon. Now let's look whether carbon is balanced. You can see here how much carbon is there? 2 CO3, 2 into 2, 4 carbon. Here it's already 4 carbon. So now if carbon is balanced, then you look for oxygen. Let us see what happens to oxygen. Here you can see how many oxygens are there. 4 into 3, 12 oxygen on the left hand side, plus 4 oxygen here, so you have 16 oxygen. And if you go here, then there are 4 oxygens for Ca2SiO4, and you have 2 into 4, 4 into 3, 12 oxygen in dolomite. So that's 16. So you're balanced the reaction. Have you understood? You have balanced the reaction. So what is the reaction now finally? The reaction is 4 calcite plus forsterite is equal to lornite plus 2 dolomite. That's the reaction. Lornite plus 2 dolomite. Here you can see lornite plus 2 dolomite. That is why instead of this it has shifted here. My triangle is not exact. And you have 4 calcite. 4 calcite. Here you see that is why the length is more here. And 1 forsterite. So that is a possible reaction. I'm not saying that's a stable reaction, but that is a possible reaction. But so this is what is called the crossing tie line. But at the same time, you can also draw this line. Do you see that? What is this line now? So what is this line now? It is calcite CaCO3 plus MgSiO3, and this will be equal to Ca2SiO4 plus CaMgCO3 plus. That's how the reaction will be. You see, this was calcite plus forsterite giving you lornite plus dolomite. You can also have a reaction calcite plus enstatite, and that should give you lornite plus dolomite. So again we go for this balancing, and you see magnesium is balanced. Magnesium is already balanced. Silicon is already balanced. So you have calcium, 2 plus 1, 3 calcium. So this should be 3 calcium. 3 calcium. So you have 3 calcium, so 2 plus 1, 3 calcium. But when we go to carbon here, you see there are 3 carbon, and here there is only 2 carbon, so plus CO2. I can't add any other phase. So I have to stick to carbon dioxide. Now then, if calcium, magnesium, silicon and carbon is balanced, then I check for oxygen to see what happens. And if I do this, on the left hand side you have 3 into 3, 9 oxygen, and you have 3 oxygen, so it's totally 12 oxygen. And on the right hand side you have 4 oxygen, and 3 into 2, 6 oxygen, plus 2 oxygen, so you have 12 oxygen. It's done. This is a balanced reaction. So you can see this reaction now gives you a different thing. It gives you 3 calcite plus enstatite is equal to lornite plus dolomite plus CO2. Now you see the 2 reactions are completely different. This is a fluid-free reaction. There is no fluid involved in it. So in this case, stabilization of lornite and dolomite is not controlled by the fluid activity. But here, the stabilization of lignite and dolomite is associated with carbon dioxide. So it depends on the fluid composition. So that is how we can write innumerable reactions based on intersections. But not all reactions are stable. Now you can ask me, sir, how do we know which can be stable? Now this can be done thermodynamically, or it could be done by something called the Schreiner's analysis. So for those of you who are interested in it, I don't think I will have the time to teach it. So I will send you a link and you can read a little bit about Schreiner's analysis. Maybe when I'm uploading it or sometime early next week, I will send you the link and you can go and have a look at the links. That's called what is called Schreiner's reaction bundle. It tells you the geometry of reactions and stability of reactions. You can do that yourself. You need a little more expertise to go around with it and you can do it. But what I'm trying to say here is important. Based on tie line intersections, we can find out the reactions. We can find out the reactions. So, say for example, remember this point here. This is CaSiO3, this is CaMgSiO3. So this point here will be CaMgSi2O6, right? And there will be a line, this is quartz. So you see, if you drop a line at 50%, diopside will lie and dolomite will lie. So quartz, dolomite and diopside will lie on a vertical line. And the composition of the dolomite can be expressed by these two, quartz plus dolomite. So I write CaMgCO3 whole twice, that is dolomite, plus SiO2, and this one is equal to CaMgSi2O6. CaMgSi2O6. Now you can see CaMg is here. I can only have to change to SiO2. So this becomes 2SiO2. And then plus, here there are 2 carbon, so it's 2 CO2. That is how should the reaction be. So if I go to the oxygen again, left hand side, you have 6 oxygen, 3 to 6. Here it's 4 oxygen, 6, 4, 10. Here it is 6 oxygen here, and 2 into 2, 4. It's 10 oxygens towards the right hand side. So the reaction is dolomite plus quartz is equal to diopside plus 2CO2. Now just before we go into the other thing, here is an important simple reaction, and I will tell you a little bit about it. This is a very simple reaction. Let's say you start with a rock containing dolomite and quartz. Let's say we take a rock which contains dolomite and quartz. Now, when you say dolomite and quartz, dolomite is a mineral, quartz is a mineral. Dolomite and quartz, the question comes, what is the proportion of dolomite and quartz? So if it's a dolomite with a little quartz, then you will call it quartz dolomite. Quartz dolomite. If I have a lot of dolomite in the rock and a few quartz grains, then you call it quartz dolomite. Quartz dolomite. Dolomite is the dominant rock. But if you have a lot of quartz but a few dolomite, then what you call it? Dolomitic quartzite. The bulk of the rock always comes at the end. Dolomitic quartzite. So say for example, if you take dolomitic quartzite and quartz dolomite, let's say we write dolomite 90, quartz 10, and dolomite 10, quartz 90. That means in molar terms, 90 dolomite, 10 quartz, total is 100, and 10 dolomite, 90 quartz. So this is quartz dolomite. Dolomite is the rock, but the bulk of the rock is dolomite. And this is dolomitic quartzite. They are two different rocks. Why? Because the composition of CO, MgO and SiO2 will be very different of the two rocks. And if you have 50-50, then you have to choose a name for it. Have you understood? You have to choose a name for it. Simple. So, now you see. I will just start this problem and then we will come and discuss this later because it's very important. Now you see, if you take quartz dolomite, it has dolomite 90, quartz 10. And dolomitic quartzite, dolomite 10, quartzite. Dolomite 10, quartzite. Now, if you start this reaction, look at this. What is happening? Dolomite and quartz are reacting in the mole percent 1:2. 1:2 ratio. Dolomite is reacting with quartz in the ratio 1:2. That means molar ratio is 1:2. For every dolomite, 2 quartz is being consumed. So, if I start with dolomite and quartz, then at one point when the reaction starts, you will have dolomite, quartz and diopside because you are producing diopside. You start with dolomite quartz. If this reaction is on, then you will have at some point of time dolomite quartz diopside. Right? But dolomite is reacting with quartz in the ratio 1:2. So now look at this. If you take this rock, what will be consumed faster? Of course, quartz will be consumed faster. So, eventually if this reaction goes on, then from here you will produce, for dolomite 90, quartz 10, you will produce dolomite diopside, quartz gone. Why? Because quartz is less and the reaction is 1:2. So you have dolomite plus diopside. Diopside is the newly formed one. Dolomite has been consumed, but quartz will be the first to consume. If you have quartz dolomite, but if you have dolomitic quartz, then you will have dolomite plus quartz reacting to produce diopside. Dolomite reacts into molar proportion 1:2, but here you can see there is a lot of quartz. So essentially you will get quartz dioxide. And this time dolomite is consumed. Now you see this. So what is happening here? The final assemblage that you are getting, you're getting through a single reaction. This one. The reaction stoichiometry does not change. But the difference in mineralogy is because the initial composition, mineralogical composition of the rock was different. That means the bulk composition of the rock was different. Have you understood? So although you have two rocks with two bulk composition, and even if the same reaction goes on, the product will be different. The product can be different. Not because different reaction has occurred. The same reaction has occurred. But because of the differences in the proportion of the reactant minerals. Because of the proportion of the reactant minerals. So what is happening in petrology, metamorphic petrology? The assemblage that is being produced is a function of the reaction stoichiometry as well as the mineralogy of the post rock. The mineralogy of the post rock. Both are important. Have you understood? We will go into more details later on. But just to give you where we are heading to. We are heading to this point that what we see is the end product. We started somewhere, then there were reactions, and we see the end product under the microscope. That you have two assemblages, two mineralogy does not mean. It could just mean that it is a product of two different rock and the same reactions. Just like here. The same reaction occurred, but just because the initial mineralogy was different, you produce two different assemblages. Now, this is one aspect that the bulk composition controls the final mineral assemblage. The final mineral assemblage is controlled by the bulk composition of the rock, even when the reaction is one and the same. There is another thing, and with this I will end this. I will just introduce you. Later on we will see what happens. Say for example, if you have quartz dolomite or dolomite quartz, there must be some fluids in it. You know, there is no rock that has no fluids. Every rock has fluid. The driest of rock has fluids. Even mantle rocks have traces of fluids. Let's say the two rocks had a fluid composition. What is the composition? Say in the dolomite quartz, XH2O was equal to 0.1. Same 0.1. Have you understood? Say you have dolomite and quartz, which you can see under the microscope, but you don't see H2O. But let's assume XH2 is equal to 0.1. Here also you see XH2 is equal to 0.1. What has happened to the fluid now? Because dolomite, which holds structural carbon dioxide in its mineralogy, since this breaks down, it liberates 2 carbon dioxide. So what happens? For every mole of dolomite from this reaction produces 2 moles of carbon dioxide. So if you started with XH2 0.1 and you're continuously producing CO2, why? Because dolomite is breaking down to dioxide, you're producing CO2, then the XH2 value of your rock is decreasing. XH2 value of your rock is decreasing. There are more complications, that we will go later. But this is very important to understand. That you started with a rock, dolomite quartz, with XH2 is equal to 0.1, but a majority of the carbon dioxide, a vast majority of it, was caught up in structural parts of dolomites. When dolomite breaks down, it releases the CO2. Where does the CO2 go? If it's a closed system, the CO2 stays inside the system. And if it does so, then obviously the amount of XH2 has to decrease because CO2 has to increase. So remember this. When you have a bulk rock like this and you have a fluid composition, so if the reaction is a fluid bearing reaction, then the fluid composition also changes. There will be more critical situations, but remember this, that you are also changing the fluid composition even if you say that there is a closed system metamorphism. Even if there is closed system metamorphism, you are continuously changing the intergranular fluids that are present in the rock. Okay, I think we stop here. In the next class we will continue with this discussion. Thank you.